So good afternoon, everyone. It's a few minutes past the hour, so I'll make a start. My name is Michael Crawford. I'm CEO of the Soil Cooperative Research Centre and hosting today's webinar. I'd like to begin by acknowledging the traditional owners of the lands upon which we meet today, wherever we are in the country, and I pay my respects to the elders past and present. The Soil CRC, for those who don't know us, the Cooperative Research Centre for High Performance Soils is our full name, is funded by the Australian Government and our 40 participants to undertake R&D to give farmers the tools and knowledge they need to improve their soil management and to improve their productivity and profitability. Our 40 partners include 8 universities, 4 state government agencies, 8 industry groups, and importantly, 20 grower groups. And with our funding for 10 years, we come together with research and industry working together to deliver research that meets the needs of our end users, the farmers. In today's webinar, you're going to hear about some of that research. Before I talk more of today's webinar to some of our housekeeping, today's webinar is being recorded and will be available for viewing on our website within a day or two. Our speaker, Dr. Yanju Liu, will speak around for about 20-25 minutes, after which there's time for questions. The way we'll operate the questions is that you type them into the Q&A box, hopefully accessible at the bottom of your screen. Type the questions in, I'll read them out, and Yanju will be able to answer them. A few advertisements whilst we're just warming up here. Upcoming webinars, we're resuming. This is our first seminar webinar for 2021, resuming the successful series that we had last year. After today's webinar, we'll commence again in July, on the 13th of July and the 27th of July. 2 weeks' time, we won't have a webinar then because quite a few have been at the National Soils Conference in Cairns. But looking at the webinars in July, you'll be able to find further details of them shortly on our website and in the next newsletter and social media. And just speaking of social media, yes, there's our website address. You can follow us on Twitter at SoilCRC, connect with us on LinkedIn at SoilCRC, or subscribe on our YouTube site, and where you can see this video and others. So back to today's webinar, to be delivered by Dr. Yanju Liu. Yanju is a Senior Research Fellow at the University of Newcastle and the Global Centre for Environmental Remediation. She has a bachelor degree in environmental science and a master's degree in mineral processing and engineering from the Wuhan University of Technology. She has a PhD from the University of South Australia, which she completed in 2009, and is now a researcher at Newcastle in environmental contamination and remediation. And in that capacity, she's leading a project in the Soil CRC, which she will speak about today. The utilisation of clays as carriers for pesticide delivery. So I'll pass across now to Yanju, to Dr. Liu, to give today's webinar. Thank you, Yanju.
Thank you, Michael.
Very good.
Slides. Yep. So thank you everyone for coming to some webinar. Today I'm going to talk on behalf of the team about the utilization of clays as carriers for pesticide delivery. This is part of our project work. So first, I would like to acknowledge all the project team, in particularly farmers group from Herberton and Burtkin farmers groups. With their significant input and discussion, we can identify the issues and challenges facing by farmers in the sugarcane industry when applying the pesticides. So we would direct our project directions in the right direction that we can deliver the right products. for the agriculture field. At the same time, I'd like to acknowledge Griffith University. The researchers there help us with some of the analysis of the materials. At last, the researchers from University of Newcastle, where most of the experiments were conducted. So starting with a bit of background about the project. As we all know that utilization of pesticides can reduce the grain loss by 30 to 40% by protecting crops from pests, insects, plant pathogens, and weeds. This is very important as the increasing demand for food supplied by agriculture. However, the pesticides applied in the agriculture field can go through different processes. For example, the microbial degradation, the photolysis degradation, the runoff, and the transportation through wind and precipitation and leaching to the groundwater. So the losses can be significant. So in this case, in order to achieve the desired biological response, we need to apply non-specific and periodically of the pesticides. It's quite important to achieve the desired biological response in order to control the pests. In consequences, there will be the pesticides applied will be greatly exceeding the amount actually required to control the target pests. This also potential to increase the pest and pathogen resistance. And also some of the chemicals, if on offsite, can be bioaccumulated and pose toxic effects to predators and pollinators. It can also potentially destroy the habitats and food sources of wildlife, such as birds. On the other hand, the pesticides residue in the soils can reduce the soil biodiversity and the nitrogen fixation, influencing the microbial community and other activities. So in this case, if the microbial community being influenced, the beneficial soil microorganisms can be influenced. So some of the soil functions will be influenced. There are several ways to minimize these pesticide issues, residue issues. One of them is improve of the pesticide formulation from the source where the pesticides apply. So for example, this is in particular for the controlled release formulation. This figure shows the conventional pesticides and controlled releasing pesticides. From this figure, we can say the controlled releasing pesticides can significantly reduce the amount of pesticides applied in the agriculture field. So in this case, the pesticides being wasted will be significantly reduced. Whereas materials has been investigated for the controlled releasing formulation. In this case, the nanomaterials or nanoporous materials is increasing attention. In this case, in particular case, that the active ingredients can be encapsulated into the nanomaterial or nanoporous materials. The encapsulated pesticides can be then applied into the agriculture field, into the plants. Through the protection of the carrier material, the pesticides can be protected from photolysis, from biodegradation, and also minimizing the leaching and volatilization of the pesticides into the environment. Of course, at the same time, we want to achieve the pesticide control efficacy. So in this particular case, in particular project, we focused on Australian sugarcane industry, which is very major component of Australian agriculture. Upon discussion with the farmers group from sugarcane industry, we identified that cane beetle is the most significant pest of sugarcane industry, which costing significant loss every year, both economically and environmentally. And for this particular issue, controlling the cane crops is very critical to minimize these damages. This photo here shows the sugarcane field affected by cane crops. We can see the plant growth is significantly influenced by the presence of the cane crops. That is showing in the photo here. This is sampled from the sugarcane farms. In order to control the cane crops, imidacloprid containing insecticides are mostly applied. This is quite commonly used active ingredients. However, as discussed previously, in order to control the pests, regularly application of the active ingredients are required. In such cases, some residue issues are rising. For example, this is due to high mobility of the imidacloprid in the water condition. So there are some surface water, groundwater is of a concern if they are contaminated by imidacloprid. So in such cases, there is a need to improve the cost effectiveness of the pest formulation to minimize these residue effects, along with other measurements that can be used to minimize the use of pesticides. There are different forms of formulations of this imidacloprid. Most of them are traditional ways, traditional liquid forms, and there are some granulars, pellets, macroencapsules that are being used to control the release to minimize these effects. At the same time, there's still some desired practical application challenges that need to be tackled through the improved formulation or carrier materials. So in this project, we thus aimed to develop a cost-effective, low residue, controlled release pesticide delivery system using the nanoporous carrier materials. We want to investigate the potential of the nanoporous carrier materials to encapsulate imidacloprid. At the same time, to investigate the loading techniques and the mechanisms between the interaction for the interaction between the active ingredients and the materials that we used. This is to achieve the desired releasing pattern that's required when we apply in the agriculture field. At the end of the project, will be evaluate some of the efficacy of the encapsulated insecticides using the material. This is a project aims that we want to focus on. In this case, we conducted an initial literature review to identify the materials that can be used for pesticide delivery. For example, porous silica nanospheres, that's nanomaterial, nanoparticles, or clay and clay minerals, the layered double hydroxides, and nanozeolites, polymer-based nanocarriers, and carbon-based materials, and also other more advanced materials that can be used for pesticide delivery. Among these different materials, we try to identify the ones that we can use in this project. Some of this has advantages and disadvantages. For example, the porous silica nanomaterial that can be synthesized successfully in the laboratory with the desired pore structure, desired size, that can be easily manipulated. However, the source of the material, precursor material chemicals, is relatively expensive comparing to others. So among these different materials that we reviewed, we tried to come up with the selection criteria for them. For example, we considered their biodegradability, their eco-friendly, and also whether there is some residue effects, and their stability, how stable they are once applied, and whether we could achieve the desired releasing behavior and the cost effectiveness of the material. Among these different category of the materials, such as polymer, lipid, inorganic porous materials, and aluminum silicate materials, with comparing these different parameters, we think this aluminum silicate materials, that's the clay materials that can be a good potential to be utilized for this purpose. This is basically due to the clay-based materials actually is coming naturally in the environment and it's biocompatible. So no adverse effects. And the porous structure. The porous structure of the clay-based materials can also be manipulated further through different treatments. So in order to achieve the desired releasing pattern. At the same time, the clay materials are relatively low cost compared to other materials. So in this case, in this project, we focused on the clay materials that can be used for pesticide delivery. So initially we sourced local clay products from local industries available in Australia. And we characterized the materials using different techniques. For example, XRD, STM, BET, SEM, FDR, TGA, these different techniques can help us understanding the purity of the material, the structure, and their morphology, and their surface area, their porous structure, functional groups, and thermal stability of the materials. So this is some of the materials that we sourced, and then the SEM and TM image of the clay minerals. With the local materials identified, we go through the treatment process. In this case, we did surface activation of the clay minerals. In particular, we manipulate the alumina silica ratio in the clay structure by the treatment. And then in this case, the surface functional groups in their structure and the clay structure being changed after the treatment actually induced the hydroxyl groups that can be utilized for loading of the imidacloprid. So this is some of the characteristics after the treatment of the clay mineral. Also, the surface area and the pore size were also analyzed. This shows that the surface area is significantly increased after the treatment. For example, at H6 is almost double of the original clay mineral. So the pore structure porosity also increased. This similar another treatment also increased the surface area from around 50 to 70. With this enhanced surface area and also the pore structure, we hope this loading can be increased after this treatment. Talking about the loading of the pedicide into clay mineral, there are different ways that can be used, such as encapsulation, attachment, adsorption, and entrapment. This different loading technique can give different material characterization, also gives the mechanism different, so the releasing pattern could be different. In this project, we try to utilize a combination of them, so to achieve the desired releasing pattern. In this figure shows the imidacloprid loaded on the modified and unmodified clay minerals using adsorption. In this case, the amount loaded on the clay minerals increased at different initial concentration of imidacloprid and at different pH conditions as well. So this is the effects that we want to see after this treatment. At the same time, there are other modifications like utilizing organic materials to modify the clay structure, interlayer structure in particularly, and then in particular increasing the hydrophobicity of the material. When this case, the hydrophobicity increased, the loading significantly increased. In this case, around 80 milligram per gram of the indichloride has been loaded. This is another modification of the clay mineral. After this, we would like to use this clay minerals and modified clay minerals to come up with the composites that we can be physically applied in the agricultural field. This is some images of the materials that we come up with. This different, we use the different polymer. In this case, we want to use the biodegradable and the environmental sustainable polymers that can be incorporated with the clay minerals, and then providing this kind of product structure that's to be applied in the field. In this case, we have been conducting the characterization of the materials. Similar techniques have been used, and we're investigating the loading and the releasing behavior, how much can be loaded and how the releasing pattern would be. This is some of the progress of the project. This project work is still going on. In particularly, we continuously investigating the loading and the releasing behavior, and also evaluate the efficacy after releasing. At the same time, we want to say the environmental behavior of the pesticides using a pot experiments. We want to investigate how they will going to behave in the soil condition. With the project progressing, we hope to achieve the potential benefits through this project. In particularly, we want to achieve the cost effectiveness in pest control. This is very important. That's the target of the pesticides application, and so we want to achieve the cost effectiveness. At the same time, soil functionability is very important to us as well. We want to minimize the residue effects, soil ecosystem, in particular soil microorganism, their functionability, want to maintain and the soil functionability. At the same time, the materials that we are sourcing, we want to be environmental friendly, achieve the minimized adverse environmental effects or environmental friendly materials to be used in the final product. Also, the last but not the least is the cost. Economic perspective of the material, we want to use low cost and also locally available materials to be used in this case. So this is a potential benefits or targets of this projects. With this brief overview of the projects and background and the progress, really appreciate your attendance for this webinar, and happy to answer any questions. If any detailed information of the project that we couldn't address here, I'm happy to receive any further contact from you that through my email address. I'm happy to discuss and look forward to hear any feedback and comments as well. Thank you.
Okay, thank you very much, Yanju. Thank you for that great overview. And yeah, you can put your video back on because we'll ask you some questions. That's it. And so I've got a message from Catherine. It seems like we're having trouble with the Q&A box, but you can type your questions into the chat box if anyone has any questions to ask. So type it into the chat box. Whilst you're doing that, I'll start off, Yanju, with a question. The application that we're speaking of here is in relation to insecticides and controlling the cane grub. Firstly, why did you choose that application, that pesticide, and can the science be applied to other pesticides and including herbicides if successful?
Thank you, Michael. That's a really good question. And for the imidacloprid, the selection is that first, it's very commonly used pesticides, not only in sugarcane industry, but also in other agriculture industry as well. So this is commonly used, and the application there is that in this particular case, as the sugarcane industry providing us sufficient support, and there is a true case that we need to consider their release pest control efficacy and also minimizing the residue effects. So this is a particular case that brought us attention. So we chose to focus on imidacloprid first, using for the material development. Regarding to the material application into other pesticides or herbicides, I think this depends on the detailed interaction between the active ingredients and the material. So in this case, the overall concept can be applied into different pesticides and herbicides, but the detailed material need to be manipulated further before its real application.
Okay. Yeah, thanks, Yanju. So there's potentially more opportunities, but more research involved. But there's a question from Nancy, but I think it might be similar to the question I already asked. So the question from Nancy was, yeah, can you use this modified clay materials to load other pesticides such as herbicides? Herbicide residues are a serious issue. So yes, we've addressed that. There's one there from Penny Cook.
Yeah.
You spoke about the materials being eco-friendly. Is there a set of measurements or standards for determining eco-friendly products so you can document it when marketing a new product?
I think currently we are just selecting the eco-friendly one first to consider how long, whether it's persistent, whether it can be biodegradable, and then the next thing is to consider whether any adverse effects are there to posing the risks from existing literature, whether there is toxic effects to the ecosystem. So this is the two parameters that we mainly consider.
So persistence, biodegradability, the adverse effects, the toxic effects. But those standards, are there standards like from the EPA or the Australian Pesticide and Veterinary Medical Authority?
I think there's pesticide authority has regulations before any pesticides being used, the detailed information that we can discuss later, check the detailed information. Don't have it on top.
Yeah, okay, good. All right. I can't see any other questions appearing. So if there are any others, you can email Yanju after the event. And I might start to wrap it up there and finish there, and just remind you to follow us through Twitter, LinkedIn, and our YouTube channel, and you'll be able to see this recorded webinar on our website in a couple of days' time, and look out there for notifications of future webinars. So without further ado, thank you very much, Andrew. Thank you to the attendees today in the webinar, and we look forward to seeing you again next time.